Yeah. Okay. Let me just share my screen. Okay. Hi. I'm audible, no?
Yes, yes, audible.
Okay. Great. Yeah. Hi everyone. So welcome to the week one problem solving sessions for the course of probability for computer science on NPTEL. Okay. Now, so yeah, what is this? Okay. Let me just introduce myself. My name is Bhavya. Okay. I am a PhD scholar at IIT Madras. Okay. So I'll be holding these sessions every Tuesday, 6 p.m. to 8 p.m. unless unless not mentioned otherwise. So every Tuesday 6 p.m. to 8 p.m. it will be happening, and what we'll be discussing, I'll just be discussing a bunch of questions, okay, which uh, uh, which will be different from the ones solved in the assignment. If you want, we can also discuss assignment questions which are already solved, which are already sorry done submitting, and then we can discuss the solution that too. If you want to do that, then you can request, and then we can do that. Okay, so uh, and please just let me know if there are any questions. Okay, I'll try my best to answer them, and if I'm not able to answer them, then I will get back to you by the next week. Okay, great. Now let's look at this course. So, what is probability for computer science for? As you know, I think a lot of you, most of you are computer science students, and you must know how important probability is. And it's used everywhere. It's used in all the disciplines of computer science, regardless of uh, what the problems are. Probability is always used. I mean, you of course know that it's used in AI, right? And it is used a lot in theoretical CS, which is my area of research. So it is used in like things like randomized algorithms, for example, Google's algorithms, and several cryptographic algorithms, okay, and cryptographic proofs and so on. They use it, and of course they are used in systems also, on actual hardware implementations also. Okay, but this course will mostly be talking about theoretical computer science. Okay, algorithm designs and analysis of algorithms, and uh, the moments, and you know uh, concentration inequalities and stuff like that. But we don't want to. I don't want to get too much into that. So, what are this week's topics? Okay, this week's topics are basics of probability, formally, like sample space. What is sample space? What are events and so on. And then we have the inclusion exclusion principle. And what do we have? We have derangements, and that's where it ends. Okay, so I hope we can move forward, because this week's content is quite simple. So here's the first question that we'll try to solve. Okay, a password consists of 6 characters, where each character is either a lowercase English letter or a digit. Define an appropriate sample space for the set of all possible passwords, okay, of this kind, all possible passwords of this kind. 6 characters where each character is either a lowercase English letter or digit. Lowercase means all the small letters. Okay, so for example, uh, AB6ZW8. Okay, this is a password, and XZ6777. This is also a password, and 12345 6. This is also password, and so on. So, but something like ABXZW9 is not a password. Why? Because there is uppercase letters and um length equals 5. Okay. So, what is the appropriate sample space? What do I mean by the sample space? Sample space is where I will draw the possible outcomes from. Okay. So, it may be a possible password. Okay. But rather, it's the space which contains all the possible passwords. So, can you try saying what the appropriate sample space would be?
So
Yeah.
first character can be selected in 260 different ways.
No, 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 no,
It
no.
could, it
No,
could,
don't give me the probability yet. I'm just saying what is the sample space. Okay. For example, like if I throw a die, okay, what are all the possibilities? Probable possibilities. All
so
possibilities. Okay, which is called the sample space omega, is 1, 2, 3, 4, 5, 6. Similarly, if I toss a coin, omega will be heads or tails. Yeah, Harsh, this Monday.
36p6.
36p6. Okay, again, not the count. The sample space is a set. Okay, you are correct in terms of uh, oh, p6. No, 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 no. That's. But I'm saying the set. What is the set? The sample space is a set, not a number.
36. Okay,
36.
no, okay,
No,
I
the
got it.
space, sample space, the
Okay,
set.
okay.
For example, heads, tails, 1, 2, 3, 4, 5, 6.
so count
Yeah.
count would be 260 raised to the power 6.
Yeah, again, don't give me the count.
Yes, yes. But
Yeah,
then
yeah,
the
go ahead. Yeah.
sample space would comprised of
Okay.
uh, like sample space would be, I mean, what are the possibilities?
Yes.
So it could either be, so basically we would be yeah, so it would be like 26 number of the correct work, I mean 26 number of the characters, alphabets, and then 10 number of the digits. So that would be A to Z, A to G, and then 0
Okay.
to 9.
Okay. 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 Ankita, says sample is lower A to Z and digits 0 to 9. Uh, Not quite. Not quite. These are the individual characters, but the sample space is the passwords itself, right? 6 length password. I think Aru Pratap Singh was raising his hand, no? So, yeah, Aru Pratap. Sorry. Uh, yeah, please say.
Sir, same. I was also seeing the same, like sample space could include the characters and the digits, but
Okay. So what you are okay? What Ankita as well as Aru is saying is that the sample space, okay, omega equals A B C till Z and 0, 1, 2 till um, 9, right? The digits as well as the English letters. So the union of these two sets. But what I'm saying is this is not the sample space, because if your password was of length 1, then I agree. Just think about this. Okay, I'll explain to you. I see the confusion. If you toss a coin, okay, the sample space, I ask you like what is the possibility of getting heads, then you will say this, okay, the sample space is heads and tails, and out of which there is one, the possibility is 1 by 2 because the sample space is 2. Okay. Now I ask you, like, what if I toss 2 coins? What is the sample space? Any idea?
4 HH, TT, HT, and then TH.
Exactly. HH, HT, TH, and TT. Now similarly, I do 3 coins, then omega is HHH, HHT, HTH, and so on. Okay, there will be like, I think, 6 possibilities. Okay. Now similarly, okay, the in so I was asking about 2 coins, 3 coins, a single coin. When I said a single coin, the sample space was either heads or tails. 2 coins, then heads, tails, and so on. Similarly, a password consists of 6 characters. A password consists of 6 characters, not a single character. If I said a password consists of a single character, what is the probability that it will be A, or what is the probability that it is ABC, and if I am asking things like that. But what I'm asking is a password which contains 6 characters. So it is akin to saying I'm tossing, say, 6 coins, and what is the possibility that, it's, HHHT and something like that. So what I mean by that is, in the question, password is length 3 and length 6. Each character is in lowercase letters or digit, right? Or digit. So my sample space is all possible passwords, which is the set of all the words W, okay, such that W, okay, is, or I can write it slightly informally also. So W is L, okay, is in L. Okay, so what I can write it as is W equals, characters C1, C2, C3, C4, C5, C6. Okay, this is my password, such that C1, C2, and so on, C6 either is a letter, lowercase letter, or, so that I can represent by union, it is a digit. So here L is English lower, okay, I'll just write it as A, B, C, and so on till Z, and D is digits, right? 0, 1, 2 till 9. Okay, so I've written it very formally, but you can also think of it crudely as sample is all possible passwords. It is not all possible letters. Okay, that is the most appropriate sample space. It's asking for the most appropriate sample space. If I was asking about, say, what is the probability that, a letter, the third letter is C or something like that, then maybe I can change, but this seems the most appropriate for this case. Okay, for the set of all possible. Is that clear? Okay, so this is a very fundamental thing that should be clear. The sample space is just all possible passwords. Is that clear? Okay, Antosh. Goel, it's clear, right? And Aru Pratap, Ankita, I think it's clear, right? Okay. Great. Okay, good. Harsh. So now that is clear, now we'll start solving things. Now we'll start. Yeah, Tathagat.
Sir, can you just repeat the last step of the problem?
Yes. This explaining the sample space. Okay. So when I said toss a coin, your sample space is all possible outcomes, that is heads, tails. When I said toss two coins, then your sample space is all possible outcomes again, which is heads, 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 tails, tail, heads, tails, tails. These are the possible events that can happen. Right? Three coins, again, heads, 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 and so on. Okay, that much is fine. Now I say, Tathagat, pick a password. Pick a password that follows these rules. I ask you that. Okay. That's my case. Instead of saying toss a coin, I say or toss two coins, toss three coins. I said pick a password. So what is meant by sample space? Sample space is the your possibilities. Okay, of what password you pick, which is nothing but the set of all possible passwords that follow this rule. Okay.
Okay.
Okay, and I can say all possible passwords, or I can formally define it as all W is the sequence, C1, C2, C3 till C6, which are the 6 characters, where each character belongs, sorry, each character belongs to L or D, where L are just lowercase digits and D are just until 9. That much is clear, no?
Yeah, sure.
Great, great. Okay. Now, let's look at the second question. Assuming that all passwords in the sample space are equally likely, compute the probability that the password contains at least one digit. Okay. Now, the possibility that you pick a password, say, apples, or the password that, APP123, anything, it's equally likely, what is called a uniform distribution. Okay. Then, what is the probability that the password contains at least one digit? So this you can try once. I'll just give you 1 minute to try this. Okay. What is the probability, according to this rule, what is the probability that password contains at least one digit? Well, saying 1 minus 26 to the 6 and 260 to the 6. That 260 is looking weird. It's going in the right direction.
Because for each character, the character could either be a in English alphabet having 26 possibilities,
Yes.
or it could either be a number.
Right.
So in total, we have 26 into 10. No, 26 plus
Ah,
26 plus 10.
yes.
36 number of the
Right,
possibilities.
right.
So the instead of 260, it should have been 36 raised to the power 6 then.
Yeah. Yeah, good, good. That's right. I'll just wait for others also to confirm. Okay, Harsh, yeah.
1 minus 26 C6 divided by 36 P6.
36C6. 26C6.
No, sorry, 26 P6. 26 P6.
But
मतलब ऊपर दोनों नीचे P होंगे.
why P?
Because
P is to deal with permutations, no?
नहीं
So,
नहीं नहीं P इसलिए किया क्योंकि टोटल जितने भी सैंपल स्पेस में होंगे
हाँ,
वो उसके भी तो परम्यूटेशंस होंगे. मतलब C6 किया तो फिर into 6 फैक्टोरियल.
हाँ, बट थोड़ा अंडर ओवर काउंटिंग नहीं हो रहा है, मतलब सो लाइक so you are saying that, okay, I think that should also work out. So if you have okay. हाँ हर्ष, तो उसमें प्रॉब्लम क्या है ना कि इफ़ यू डू 26p6 तुम लेटर रिपीट कर सकते हो, यू आर नॉट टेकिंग दैट इनटू अकाउंट. P मतलब यू आर टेकिंग वन लेटर ओनली वंस, नो.
हाँ, नहीं नहीं, पी मतलब कि जितने भी ये होंगे, क्या होते हैं, जितने भी अलग अलग टाइप के ये बनेंगे
हम्म,
6 लेटर कॉम्बिनेशन, उसका भी तो हम ये करेंगे, अंदर ही अंदर मिक्स करेंगे।
हाँ, बट रेपिटेशंस तो हम नहीं ले रहे हैं ना अकाउंट। सी, ये
नहीं
जो है
बट
ये 26
हाँ,
साइज का सेट है ना?
यस,
सो यू सेट 26p6 है ना? बट अगर मैं बोलूँगा 26p6, यू आर सेइंग हाउ मेनी वेज आर देयर कि आई कैन पिक 6 letters from here and rearrange them. How many rearrangements are possible? How many arrangements are possible? For example, I can take A, B, C, E, F, G. Furthermore, I can say कि A, C, B, E, F, G, and there are so many rearrangements possible, है ना?
यस,
But तब you are not taking into account all the passwords where A is repeated, B is repeated, C is repeated, and so on. So A, B, B, C.
ओके ओके,
Okay, this is never taken into account.
आई गॉट इट।
अच्छा, ठीक है। सो हाँ, मतलब हाँ, सो येट परमिटेशंस का बात नहीं है। अगर लेट्स से यू से कि 26C6 बोला, तभी भी यही प्रॉब्लम होगा। अब अरेंजमेंट्स तुम काउंट कर रहे हो, कर रहे थे पहले, अब अरेंजमेंट्स काउंट नहीं कर रहे हो, विच इज़ स्लाइटली मोर रॉन्ग। एंड बट फिर ओवर काउंटिंग तुम नहीं ले। हाँ हर्ष।
फिर 1 - 26 की पावर 6 डिवाइडेड बाय 36 की पावर 6।
एग्जैक्टली एग्जैक्टली।
यस,
ओके ओके ओके। So I'll make this clear for everyone. Okay, so here is the logic. So you have 6 places. Okay, so before this, let's see what do we need to calculate. So we need to find the probability that um, at least one. What is the problem? Computer probability, the password contains at least one digit. At least password contains, okay, password contains at least one digit. Okay, is, I mean, we all know, right? The number size of the favorable outcome set of favorable accounts divided by the sample space, right? That's what we say the probability is. And इस केस में what is the set of favorable outcomes? It's exactly again this, all the passwords with at least one digit. Okay, now this is slightly difficult thing to compute. Okay, this is a slightly difficult thing to compute because why? Because well, you need to take into account like one digit, two digit. What if there are 2 digits? What if there are 3 digits? What if there are 4 digits, and so on? So let me call this guy event A. Okay, event A is the event when the password contains at least one digit. So what is event A complement? The opposite event. The opposite event is saying, the opposite event is saying password does not contain any digits. Now the problem has become much more simpler. Okay, A complement is password does not contain any digits. Okay, now this we can calculate very simply. Okay, because it's just all the passwords, okay, which contains only letters. Okay, and we know that the probability A is 1 minus probability of A complement, right? So this it's you've done it in high school probably. Probability A is 1 minus probability A complement, and 1 minus probability A complement is probability that the password does not contain any digits. So probability of this set, let me call it the favorable outcomes, no, for A complement. So the size of the set W such that W uh, contains only letters. Okay, divided by the sample space. Okay, the sample space, we already know what it is. It is all the possible combinations of letters and alphabets of length 6. Okay, now here's what we do. Now let's find the sample size of sample space first. Size of sample space. Okay, now there are 6 positions. Okay, in each of the 6 position I can either put A, B, C till Z, or I can fill it with 0, 1, 2 till 9. Okay, so total how many possibilities are there? 26 plus 6 plus 10 is 36. Okay, so there are 36 possibilities for each of the places. So the first guy can be filled in 36 ways, second place can be filled in 36 ways, third place can be filled in 36 ways. So total number of ways, number of passwords is 36 times 36 times 36, 6 times is 36 to the power 6. Okay, this is like the permutation combination we learned in school. Okay, but in case you just want to revisit, then just let me know. And what is the probability? Okay, then what about this probability? W such that W contains only letters. Okay, now this set, okay, has again 6 places, and each of the places can have one of the many, letters A to Z, and these letters can repeat. So every time there are 26 possibilities, 26 possibilities for each of them. So total ways equals 26 power 6. Therefore answer equals 26 power 6 divided by 36 power 6. Okay, 1 minus. Okay, I won't write answer, let me write P of A. Okay, and I think this is a pretty large number. I think it will be 1 minus this will be something like 98, 99% or something. Okay, but I hope this is clear, right? Anyone, is there any issue? Just let me know. Yeah, Aru.
Sir, I have a general doubt here, sir. While calculating the sample space, why do we multiply? Like, I have a doubt in this. Like, I was thinking to multiply, but I was then thinking like to add like 36 plus 36 plus 36. So it was my basic doubt
Okay,
here.
okay, okay, sure. So here is again, let me simplify the case. Let's look at the heads tails business. Okay, so let's look at like two tosses. Okay, let's look at two tosses. So when we say there are two tosses, what is omega? Omega is heads tails, tail heads, heads heads, tail tail. Right, these are the possibilities. Now, and I say 3. Okay, then let's say I say 3 tosses. Then what is omega? Omega is heads heads heads, heads heads, tails, head tail head, head tail tail, tail head head, tail head tail, tail head, and tail tail tail. Okay, now these are the possibilities when you do 3 tosses. Okay, now what is the size of omega? Size of omega is 4. And what is the size of omega? Size of omega is 1 2 3
8.
8, right? 8. Now the question is there a simpler way to do it? What if I say, I tell you to do like 10 tosses? Then what is omega? That will be very difficult to enumerate it, one by one. So the general, so and rule about about counting with repetitions. So this is the part of combinatorics which says counting with repetitions is that if you are filling, you know, places, okay, and from a set, okay, for example, head, tail, head, and so on, okay, then the number of ways to do that, okay, is always, you multiply. So what I mean by that is, if a is the number of ways, so if a is the number of ways that a happens, and b is the number of ways that b happens, then what is the number of ways that a happens and b happens? This is always multiplied. Number of ways is the number of ways a happens, which is small a, times the number of ways b happens, which is small b. Okay, this is the fundamental rule which we learn in combinatorics. Okay, if is that fine? First of all,
So, sir, it means like if we have independent events, so we can multiply the independent like.
yes, they need to be independent. That is another important point. In this
Yes.
case, we know that they are independent. Okay. Now, the fact that you can repeat it is what makes it independent here. So the fact that I make a head here, and the next I can make it head or tail, it does not depend on whether I filled the previous one with head or tail. Okay, so they are independent. So now the idea is that any place, okay, the number of ways that head happens, the I either I put it head or I put it tail. This is head or tail. This is again head or tail. This is again head or tail. Okay. Now, what is the total number of possibilities? It is there are two ways to fill this, times what is the number of ways that head or tail happens in the next one. So times two ways to fill this, times two ways to fill the third one, and times two ways to fill the fourth one. Then so it's just 2 times 2 times 2 times 2 times 2 times 2, which is 2 power 6. Okay, so similarly 3 tosses is nothing but 2 power 8, 2 power 3, and this is nothing but 2 power 2. Because these events are independent, okay, counting with repetitions, when you do counting with repetitions, you can simply, multiply these possibilities together. Okay, now look at this case. There are 6 places. Okay, where is omega? Okay, there are 6 places. Okay, yeah, just one moment, I'll just complete this. There are 6 places, and each of the place I can fill with 26 possibilities plus 10 possibilities, 36 total. So it becomes 36 times 36 times 36 times 36 times 36 and 36. So it's 36 power 6. Previously, head tails was 2 ways, so head or tail. So 2 ways times 2 ways times 2 ways times 2 ways, and so on. Okay, yeah, got it. No, so that's why it becomes 36 power 6. Yeah, Tathagat. Oh, got it. No, okay, great.
Sir, that means that stands like there are total 26 letters. Okay,
Huh.
those 26 letters and 10 digits,
Hmm.
they are to be placed in 6 different places.
Yeah.
So while remembering the repeating nature,
Hmm.
we total 36 items, and it's just getting repeated for 6 times. So that's why 36 to the power 6, right?
Yes. That's
Okay.
right. Yes, exactly. Good. I mean, if you love formalism and mathematics, then another way that you can see it is, this is just a Cartesian product. So you can see it as um, you can see it as the set A B C to Z union digits, 0 1 2 till 9. This entire set is if this set is x, then what we are finding is x power 6. I mean, if you like this kind of,
Yes, mathematics is favorite
yeah.
subject for me. Yeah, mathematics is my favorite subject.
Oh, great then. Yeah, great. Then this is Tathagat, you will notice that this is nothing but the
Yeah,
Cartesian
this
product.
is the Cartesian product. Yes.
Yeah, right?
Yes. Nice.
Yeah. So that is another way to view it. Okay. So it's that again you'll get 36 parsecs because this is 26 plus 6, okay, and 36 parsecs. Right. Okay, great. Good then. Let's move on. Okay, what is the time now? Okay, this question I won't be doing. Just note it down. Maybe we can discuss this next class. Okay. Uh, it's just an application of probability into hashing. Okay, and okay, so let's move on. Okay. Okay, here is a very interesting problem. Okay, I want you guys to think about this. So the question is, you are a participant in a game show where you have reached the final level of the game. Okay, you are given the choice of three doors. Behind one door is a car, behind the other are goats. Okay, there are three doors. There are three doors. You don't know what are behind the doors, okay, but there are three possibilities. Okay, there is a car, or there is a, don't mind my bad drawing, okay, and problem of the movie 21. Oh, is it? Okay, then wait, who is it? Harsh. Okay,
So,
yeah, Harsh.
uh,
Harsh, no. Okay, please don't reveal the answer then. Okay.
okay.
Oh yeah, okay. Tathagat also, you've seen this.
Yes.
Okay,
It's
okay.
a famous fallacy kind of.
Oh, okay,
Okay.
okay. Yeah, yeah. Okay, great then. Then please don't reveal this. Okay. So the
That's
the
you.
question goes to the rest of you. Okay. I don't know the possibilities behind the three doors. Okay. Now there are two. There is door one, door two, door three. Okay. Here, just for context, I've shown a car behind door one that you don't know. Okay. So you pick a door, and let's say you pick door number one. Okay. You pick door number one. Okay. Now, after you pick door number one, the host definitely knows what is behind the doors. Okay. And he opens another door. Okay. Let's say this was the configuration. He opens a door and he opens this door, let's say, and he shows that, okay, there is a goat here. Now he asks you, do you want to switch to door two? He gives you an option. Do you want to switch to door two, or do you want to stay in door one? He asks you this question. I hope the question is clear. Just let me know if you want me to clarify it. You come to the game show, you pick door number one. The host opens one of the other doors. It could be two or three. And when he opens the other door, let's say three, he shows that there is a goat inside. Now he asks, do you want to switch to door two? Or do you want to switch to stay in door number one? Or if he had opened door two and showed the goat, he would say, do you want to switch to door three, or do you want to stay in door one? Okay. Now the question is, would you want to switch the door, or would you want to stay in your door, or you feel like there is no use of switching at all? It's equally likely that you will get the car. Okay. So here's the question. I hope it's clear. Just let me know. Yeah. Now, just you can, it's okay. You can just guess about this. Like, what is there any advantage to this? Okay. Oh, one moment. Is hello? 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 Am I audible? Hi, sorry, I lost Wi-Fi connection. Hello, am I? One moment. Yeah, am I audible? Hello, hello. Yeah, am I
Yes,
audible?
yes, you're audible.
Oh, okay, okay, okay. Yeah, sorry, I lost my Wi-Fi
Yes.
connection. I'm joining via hotspot. Just give me a moment. Yeah, just think about the question. Okay. Yeah, I think it's. Am I audible now? Hello, hello.
Yes, sir.
Okay, okay, great. Okay, okay. I'll just try to connect here. I'll just share my screen here. Is my screen visible?
Yes, visible now.
Okay, great. Problem is my recording is not working for some reason. Yeah, so yeah, in parallel, I just ask you guys. So is the question is clear? So what do you think? What do you guys think?
So initially, it seems that switching may be initial. This is the initial thought because,
Okay.
initially, I am having the probability of getting a car is 1 out of 3. But then, if one door is being revealed, then the probability of having car becomes 1/2. But then this is not correct. So I mean, then I would like to make a switch, but I need to take this point
Right.
into the consideration. This is not this may not be not right because what is the probability of getting a car is initially what is the probability of getting a car is that I have a car
Hmm.
what, whose probability is 1/3 because it is there in one box, but the remaining two boxes I have goods.
Yes.
So that would be then what that probability is. So in the remaining boxes, I am having the same stuff.
Yeah.
So that came out to be 2/3.
Right.
Is
Right.
it? So then the value came out to be 1 by 3 into 2 by 3. So the value is 2.2 by 9. I'm not sure. Yeah, 2 by 9. 2 by 9, say. And if one door has been revealed,
Huh.
then what is the probability of having a car is 1 by 2 and multiplied by that the other door is having, or it is known. No, other door is also having a cord.
Okay,
Is
okay,
one. So
okay,
that value came out to be 1 by 4.
okay,
So now
okay.
which one is bigger? That value 2 by 9 or 1 by 4?
Okay, okay. 2 by 9 or 1 by 4. So um, is it advantageous to switch or not?
So this, I mean, calculation. I know.
Huh.
I do. I have not seen this problem, but so calculation says that 2 by 9 value came out to be 0.2 and
Okay,
0.
Arup Pratap says switch. Okay, yeah, 2 by 9. Okay, 0.2. I think your analysis, Goel, you're making it more complicated than it needs to be. Okay, slightly more complicated. You're looking at a lot of conditional probabilities. Okay, so which need not be the case. I mean, okay, so okay, so should I wait for some more time for you guys to try, or should I reveal the answer? Okay. Anyone wants more time to think about the question? Okay. Did I get a message? Can you explain the question again? Yes, Ankita. Okay. So here's the question. Okay. So okay, I'm sorry, my camera is off. Okay, so I can't because of the network issue. But yeah, so uh, so imagine that you are in the game. Okay, and basically the objective is to win a car. Okay, how many cars are there? There is only one car. And how many goats are there? There are two goats. And how many doors are there? Three doors. Now there are three doors, and you out of which, I mean, behind each of the door there is either a goat or a car. Okay, so, and these doors are labeled 1, 2, 3. Now you pick a door, say a door number 1. The host does not open this door. This is still a mystery to you, what is behind door 1. Okay, you just take a random guess, because your guess is as good as mine. Okay, only the host knows what is behind those doors. Now you pick door number 1. Now the host does something interesting. Okay, the host opens one of these doors, 2 or 3, whatever, but let's say he opens door 3, and behind door 3 he shows that there is a goat sitting. Okay, he reveals this to you. Now he asks you, do you want to stay with your original option, door number 1, or do you want to stay with your original option, door number or do you want to switch? So the question is, do you want to switch or not? Now it may so happen that maybe there was a car behind the third door. Okay, and this is here, so you are 1 here. So it may so happen that there was a goat behind door 2, and he opened door 2 and showed that there is a goat. That may be the reason why he did not open door 3. But definitely when he opens the other door, okay, one of the two doors, he always shows you a goat. Question is, do you want to switch or not? Oh, okay. Can you see my, okay, you can see my screen, right? Okay, great. Okay. For a moment I thought, just a moment, can you switch? Kaushik is also saying switch. And so if he opened the door, he revealed what is behind the door, and told to switch immediately. Or told to switch immediately. No, he first reveals what is behind the other door, not the door that you chose, and then he asks you whether you want to switch or not. Okay. Okay. Good. Great. So, okay. So, Ankita, okay, switch. Kaushik is also saying switch. Okay. So, Ankita, is it clear? Now, is the question clear now, at least? Is someone speaking? No. Yeah, a bit. Okay. Okay. So the point is, Ankita, that the host, okay, is not opening the door you chose at first. Okay. Whenever you chose a door, he's opening one of the two other doors and revealing a goat behind that. So now you have some new information. No, you have some new information that there's a goat behind one of these behind one of the other doors. So will switching be to your advantage to win in order to win a car? So basically, um, that is what I would say. Okay, I think I'll start recording in my iPad and stop this particular recording. Okay, this one is not. Yeah, this was very unforeseen. Let me try a Durum. How many chances given to switch? There's only one chance to switch. Yes. Yes. There's only one chance to switch. Yeah, I should have clarified this. Now, if you once you switch, okay, once you switch, uh, now it's done. You're now it's finally done. Okay, you can't switch one more time. Or if you say I want to stay, you have stayed. You can't switch again. And then he just reveals to you what is behind your door. Yeah, I should have mentioned this. That's a good question. Yeah, Renuka Devi says two doors now has equal probability. Okay, so yeah, Renuka, I think what you're saying is, um, when you open a door, so when with the new door opened, the remaining doors is as good as earlier, right? The choice there is no choice. Okay, okay, it's clear no now, Ankita. Okay, so I think I'll. Okay, there's some really weird stuff happening in the laptop. Okay, I'll start a recording here. Oh, did I? Screen broadcast. How do I? Oh, I can't record parallelly, is it? Okay, great. Just sorry for this delay. Okay. One moment. Okay, yeah, I think it'll work now. Okay, so what is the name of this Google Meet? Google Meet information. SB80. Okay. Yes. Okay. I need to sign in. Okay. SPA TIT cent RPM. Recording हो रहा है ना OBS का. Oh, it's showing me. अरे वो क्रोम से हो ही नहीं रहा है, कुछ भी नहीं हो रहा है. 1 मिनट दो तो आई थिंक होगा. आप अब होगा आई थिंक. यहाँ से हो रहा है. Okay, I'll just be parallelly explaining here. Okay. Um, so so here's the idea. Okay. So yeah, I'll tell the flaw in the logic also. For example, if there are 3 doors, okay.
Sir, I am not audible, sir.
Oh great. Oh, sorry. Sorry. Yeah. So if let's say there are 3 doors, okay, 1, 2, 3, and okay. So there are 3 doors, 1, 2, 3, and the logic would be that okay, fine. He revealed to me one of the doors, right? He revealed to me one of the doors. Now, even if he showed me a goat here, and I didn't know what is the probability of winning. It used to be 1/3. Okay, it used to be 1/3. Now he revealed that there is a goat behind door number 3. Now I am asked like, should I stay here or should I switch? Well, even after I showed a goat, there could be a car here and a goat here, or a goat here, a car here, and a goat here, or a goat here, okay, and a goat here. So this or this. So the probabilities are equally likely. The probabilities are equally likely. So new probability equals half. So even if I switch, I'm still gonna get half. I'm still going to get half. I mean, even if I switch, it does not matter whether
it
I
does not matter
switch
whether
to
I switch to
the next new door.
the next
Okay,
new door.
because the
Okay,
probability is still
because
half.
the probability is still
But
half.
this is
But
flawed.
this is flawed.
This is what you'll expect.
This is what
No,
you'll
that
expect.
even
No,
on
that
switching,
even on
there is
switching,
no
there
new
is
thing.
no new
But
thing.
the
But
fact
the fact
that
that
I switched.
I switched.
Okay, the fact
Okay,
that
the fact that
sorry, the host has
the
revealed a
host has
goat
revealed a
is
goat
going to play the
is
main
going
role
to
here.
play the main role here.
Okay,
Okay,
so
so
I'll just
I'll
pause.
pause. I'll
Remove my
remove
mic
my
from here, and yeah.
overlap. Overlap voice is coming, and we
Okay.
cannot hear anything
Oh
clearly.
no. Okay. Okay. Is it better now?
Yes, it's better.
Okay. Okay. Great. Okay. Good. Finally. So so okay. Sorry. Then I'll explain it once again. Okay. So you have three doors. Okay. Yeah. I'm very sorry for this. There was a very bad technical error. Okay. So there are three doors, one, two, three, and the usual logic would be the probability that I win a car is already 1/3. I don't know what is behind the two doors, right? There's only one out of three doors from which I'll win. Okay, good. But he revealed to me that there's a goat here. Okay, so now there could be a goat here and a car here, or a car here and a goat here. Then I'll say the information that the host has given me is useless, right? Because there could be a goat and car, or a car and goat. So the probability of winning a car on staying will be half, and on switching will still be half. That's the logic with which you'll think, right? That's the logic with 99% people will think. And there's no use in switching. So what you will say is no use in switching. But that's the trick here, that this is not true. Okay, there is a clear advantage. On switching. You must switch. Now let's see why. Okay, let's see why. Let's look at the three possible cases. Okay, door 1, door 2, door 3. And this is case 1, this is case 2, and this is case 3. Let's look at each of these cases. Okay, switch, don't switch. Okay, so the first car, let's say the first one has car behind it, and there is a goat, and there is a goat. And the next one has a goat. And the next possibility is that the second door has the car. And the third possibility is that the third door has a car, and the remaining have goats. Okay, so let's say you had chosen door 1 first, obviously, right? So you chose door 1 first, and the host shows either door 2, opens either door 2, or opens door 3. Okay, now let's say he opens one of the doors and you still see a goat. You see a goat. If he opened door 2, then he will have door 3 left as an option. If he opened door 3, then you have door 2 left as an option. In either case, if you switch, what are you going to get? If you switch in the first case, oh no, what happened now? Okay. If you switch, what are you going to get in the first case?
Got.
Good. Right? And if you don't switch, well, great, you get a car. So it already looks like, it looks like you'll be saying that if you should not switch because you're getting a car. But let's look at the other cases also. Okay. So in the other case, in the second case, you have chosen a goat actually. You don't know that, but you've chosen a goat because you've chosen door one. What does the remaining doors have? Car or a goat, one car, one goat, right? And door number two and door three. But the host is opening a door which has a goat. Definitely. So you know that he's going to open this door. So what is behind the other door? A car. So what happens if you switch? If you switch, you need to switch door 2 because door 3 is already opened. And if you switch, what do you get? You get a car. And if you don't switch, what do you get? You get a goat. And then finally the third possibility. Okay, again you have a goat. Oh, this is identical to the second case. Now the host needs to open this door because this is the only other door. Okay, this is the only door which is not door 1 which contains a goat. He needs to reveal a goat, right? That's the rule. So he reveals the goat, and then the door 3 has a car. And now you switch, let's say. If you switch, then what do you win? You win a car because you can't choose door 2, it's already revealed. You need to switch to door 3 which has a car. And if you don't switch, what do you get? You get a goat. So if you switch, there are 2 out of 3 cases where you get a car, and if you don't switch, there are 1 out of 3 cases where you get a goat, where you get a car. So probability of getting car when you switch is 2 by 3, and probability that you get a goat when you don't switch is 1 by 3.
Can this also be solved by Bayes' theorem?
You can
The
solve it by
tree structure?
you can do it by Bayes' theorem, and
Okay, because I did it, but I wasn't getting the answer.
you can do it using Bayes' theorem, but you need to calculate the conditional but you'll be internally doing the same thing because finally you are computing the conditional probabilities, right? And
Yeah.
yeah, it'll become slightly more complicated. That's what I think, because now you need to get the intersection of the events, right? What if there is a car and a goat and so on? Car behind the first door and a goat behind the second door, and it'll be more conditionals. So I think this way would be more simpler. Okay, Harsh? Yeah, but is it
There
clear?
is,
Yeah.
yeah. So the last value needs to be modified. I guess the probability of getting a
Oh,
goat when
sorry.
you don't
Yes,
switch.
yes. This is car. Yeah, thank you. Okay. Probability of getting a car when you don't switch is 1 by 3. So why would you not switch? You would switch, right? You will switch and get a probability of 2 by 3 of winning. Is this clear to everyone? Okay, Tathagat. Okay, Tathagat gave. Okay, thank you. Okay, Ankita, clear, good. Okay, yeah, the rest. Okay, Renuka is fine. Okay, Aru Pratap. Great. Okay. Yes, Tathagat. Yeah. This is called the Monty Hall problem. Because there used to be, there was a game show by a statistician as well as, a casino enthusiast called Monty Hall, who was somewhat of a celebrity, and he had posed this problem. And in a show or a newspaper article that I don't remember, but he had posed this problem, and most people thought that there would be no advantage in switching, but there was one woman, okay, who actually said that there is an advantage in switching, and then published it in a newspaper. That's what I believe. And people opposed her like anything. Okay, there were so many criticisms, but she, you know, stood her ground, and actually her logic is sound. Okay, it actually is more advantageous to switch. Now, now that okay everyone is clear, let's make it more interesting. What if there are more doors? Okay, let's say there are k greater than 3 doors, okay, 10, 100, 50, whatever, instead of 3, and the host opens k minus 2. So you choose, again the rule is same, you choose one door. Now host opens k minus 2 other doors, okay, with goats. How advantageous is it to choose your switch your choice? So what are the calculate the probabilities again? So see there are 10 doors or 100 doors, okay, instead of three doors, and the host opens k minus 2 other doors. Okay, so let me again draw a picture. So k is greater than 3, so let's say so many doors, and you pick door 1. Okay, you pick this, and total there are k doors, no, and the host opens, k minus 2 doors. So there is one door remaining. Okay, there is one door remaining to give you an option to switch. Let's call it, without loss of generality, door 2. Okay, k minus door, and all of these have goats. That's what he reveals to you. And now I ask the same question: is it advantageous to switch? It looks like it's more advantageous to switch, looking at the previous problem. No, but how advantageous? What is the probability? Okay, try to find that out. So you need to find the probability that, try to use the same kind of table method. Think of what would happen to the table if there are more doors. Probability that
That basically, we have the probabilities coming up to be 1 by k for being correct regarding our switches.
okay.
But now if we switch in this case, this will the probability will get increased to k minus 1 by k.
K
So
minus 1 by k. Okay,
yeah, so according to me the switch is advantageous.
great. Okay. Seems to be correct. Okay, let's see. Yeah, looks fine, I think. Okay, so anyone else have any guesses
I didn't understand your explanation.
on this, right? The second part B.
Yeah.
Oh, you didn't understand which part? The question.
K minus 1 by k.
Oh, okay. No, that is fine. That I'll explain.
Okay.
Okay, that I'll explain. Okay. Okay, great. But the question is clear to you, no, Harsh? The part B
Yes,
question.
yes.
Okay, great. So let's see what happens. Okay. So if I have, let's say, 4 doors instead of 3, then my car, goat, car, goat, um, goat, car, goat, and goat, car. These are the 4 possibilities, right? If there are 4 doors, no, and now if I have say, what about switch and don't switch? Okay, you always choose door 1. And in the first case, if you choose car 1, the host will do k minus 2. So he'll leave you one door. Okay, so no matter what door he leaves you, like he could have chosen these two or whatever, whenever you switch you lose, and if you don't switch you win. Okay, now let's look at the remaining cases. Okay, this is case 1, this is case 2, this is 3, case 4. Okay, let's say um, you chose door 1, and you chose and the host opens, you know, two doors that have k minus 2, which is 2, right? Two doors that have goats in them, means he needs to open these two. If you switch, you will definitely win, and else you'll lose. Again, if there is a goat behind your own door and he opens k minus 2 doors which have goats, so he'll need to choose this door and this door, and you'll win on switching, and you'll lose if you don't switch. And again, you know, he'll need to open these two doors and leave you one door, and it'll have that car. If you switch, you'll win, and otherwise you'll lose. Now we see a clear trend. Now if you have door
Yes.
1,
Just repeat the number one case, please. Other three are clear.
yeah, number 1 case, okay, number 1 case is behind door 1 there is a car, okay, and the
Yes.
remaining are goats. Now
Yeah.
the host will open two doors that have goats behind them. Okay,
Okay.
he could have opened these two doors, or these two doors, or these two doors, right, or these two doors, right. But no matter which set of two doors he opens, the remaining door will always have a goat behind it. If he opens these two doors, then your switching option, the option will always have a goat here. If he opens these two doors, then the remaining option will always have a goat. It does not matter, right, Tathagat?
Yes.
It
Now
will
get
always
it.
have a goat. So if you don't switch, you already have a car. If you don't switch, you already have a car. So you win if you don't switch,
Okay.
and if you switch, you will definitely get a goat. So you'll lose. Yeah, Harsh.
But other than doing this table, I think there's also another logical explanation for this because goats are more than the car. Obviously, there's only one car.
Yes.
So the number one position, door number one position, it will occupy more spaces in the sample spaces. Like in door one, the position for door one, goats will occupy more in the sample space. So naturally, there will be more goats in door one in the sample space, as we can see here and in the previous example. So if we switch, we will always get not always, but there's a higher odds of getting a.
Yes. I mean, yeah, exactly. I was going to talk about the intuitive process of this also. Thank you for mentioning.
Yeah, I was thinking about that.
So yeah. The intuitive process is like, first of all, yes, the number of goats are more, and when the host has revealed a goat, okay, this is the main intuitive process. When the host, you feel like the host is, he host has a huge advantage of knowing what is behind the door, okay, but the host is not all that powerful because he knows what is behind the door and he's supposed to open the door which has the goats. That is causing the problem for the host, okay. So he definitely needs to open a door which has the host, and in most cases, okay, when the car is not yours, every time he opens the k minus 2 doors, you'll always land up with a car. I mean, in the other door. In all the cases where you don't have a car, so the car is either here or in the door which is not opened by the host, because the host is forced to open a door which has goats. So this is the intuitive process of thinking about it. Yeah.
So can we solve it slightly more formally and without using the table? Like, can we compute that how much probability reduction is there in the light of the evidence that the one door is having the goat?
Sure.
I mean to say that can we apply the Bayes theorem here? Like say, can we compute the probability of A by B, wherein A is the probability, A is the event that the first door is having the car, and B is the evidence that the goat has appeared.
Yeah, yeah.
And I think we can do that also. So
We could do that, okay, but I feel
mm,
like there would be too many conditionals. I would personally say that the calculation would
I
be a bit hairy, I think.
I don't know, but I tried it and I got the same value.
Oh, you
Like
got the same value.
probability of, yeah, so probability of A by B is equal to the probability of joint AB divided by the probability of B.
Yes.
And the calculation is not that long. If you can write this calculation,
No, no,
then
but what if you have k many doors? That's what I'm.
for k doors also, I will get the same value.
Okay.
Like what is the joint probability that one door is containing the car and all other remaining ones are having the goat. So that value came out, joint probability came out to be what? K minus 1 by k into k minus. So the value came out to be the same, k minus 1 by k.
K minus 1 by k. Okay, okay, okay.
Yeah.
Okay,
Yes,
great,
yes.
great, great, great. Okay, okay, okay. Okay, then the process is not as complicated that I was thinking about. So what you want to do is you want to find the probability that there is a car behind door 1, given that
The
uh,
car three, behind the gate 3, there is a goat, right? Behind the gate 3, there is a goat. So if we compute this probability, then that would be, we can simply use base here.
given that door behind door 3 there is a
There is a
goat.
goat.
But see, there is some information hidden here, no? So, okay, but you can technically do it. But you say behind goat 3, you need to consider like behind goat 2, there's a goat also, right? Because the host can open either door 2 or door 3.
But then, what evidence do I have? I have the evidence that the gate 3 is having a goat,
Yes.
right? So if I take that evidence here and say the root 3 is having a goat,
Huh.
and if I compute that probability, that how much reduction in the uncertainty is there.
Yes.
So that value came out to be what? The joint probability of car multiplied by the probability of having a goat behind the gate 3 divided by the probability of having the goat behind the gate 3.
Okay.
And so the first value came out to be what this joint thing is, that the probability of car uh, multiplied by that thing. So value came out to be 1 by 3 and then
Okay.
into 2 by 3 divided by the 1 by 3. And I don't know, somehow the value is coming as
Okay.
2 by 3 here.
Okay, 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 great. Okay, okay. Yeah, yeah, okay. Um, okay, I don't want to get into the calculation because I think it will become hairy. But yeah, I'll just look into it, okay? I'll let you know.
Sure, sure,
Yeah, yeah.
sure, sure, sure.
But an alternative, I think, would be, I think a cleaner process could be by using induction. That's what I think. Induction over the number of doors. You do your exhaustive analysis in 3 doors, and you propose for k doors it's k minus 1 by k, and what you do is you calculate the probability for k plus 1 doors, given that it's, so you reduce it to a smaller problem. That could also be another way, possibly, which I would say would be cleaner. But yeah, let's see. Okay. So anyhow, uh, so probability 2, probability 3, and so on till sorry, what am I saying? Door 1. Okay, there's door 1, door 2, door 3, and so on till door k. What you'll observe is now, again, this is car, goat, goat, goat. How many cases will be there? There will be k many cases, right? Because there are k places where this car can go, and then the remaining are goats. And what you'll observe is, okay, if you switch, don't switch, you'll get the same answer that, okay, if there was a car behind door 1 and he's opening k minus door, I'm left with one goat. So on switching, I will get a goat, so I'll lose. Otherwise, I will, if I don't switch, I'll win. Just in the first case, all the remaining cases, I mean, it's identical. He'll need to open these doors, and I'll get a car when I switch. And then otherwise, I'll lose. Again, he'll need to open these doors, and I will win. Else, I'll lose, and so on. So, in k minus 1 out of the k cases, on switching, I will win. Okay. So, probability of winning when I switch is equal to k minus 1 outcomes where I win divided by k. So, this is what you get. Now, you can say, like, what if there are 100 doors? Then what is this? This then probability of winning on switching is 99%. So as the number of doors increases, the chances of you winning increases. And it seems counterintuitive when you first look at this question, but then you see the way that this question is designed, and then you understand that, oh, okay, once the doors increases, and the goats also are increasing, and the host is forced to choose the doors which have goats, then you can see that, okay, on switching, this information is important to me, because the host is exactly not opening, in most of the cases, in 99% cases, is exactly not opening that door which has a car there. So hence, yeah, this is the final answer. Is that clear? Okay, great. Yeah, Harsh.
What was the name of the problem that you?
Oh, yeah, sorry. This is the Monty Hall problem.
Okay.
Okay.
Thank you.
Yeah, Arupratap.
So, sir, in the above question, which was including four doors, so the probability of we get by switching is 3 by 4.
Let's see. It should be 3 by 4, yes. See, there are 3
So,
wins
sir,
out
if
of 4 cases,
yeah,
right?
yeah. So, sir, if we increase the number of doors,
Yeah.
but the host opens less number of doors, so then switching can
Yes, yes. That's a good
around
question.
that.
You can parameterize this problem further. Good question.
Like
So,
if we have 100 doors and the host open 50 doors,
50
then
doors.
switching might be beneficial. We want to create
Yeah,
that.
yeah, 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 yeah. Yeah,
And
good question. So this is a nice exercise you guys should try. So what if the host opens like k by too many doors? Okay, instead, then is it to your advantage to switch? So yeah, that's a very good question. You can parameterize this problem further. Okay, good. And then you can further ask, okay, if it is advantageous, then what is the point where it stops being advantageous? Like, what is the value of that m, let's say, where m doors are opened by the host, where exactly it starts becoming non-advantageous to you? So that wherever that lies, you know. Okay. So yeah, good question. Okay, so here's a very simple question. Okay, but it is important to build a fundamental understanding of probability. Okay, so here's the question. So Akshay and Bella are playing a game whose rules are as follows. Okay, each of them places a bet on whether a coin toss results in heads or tails. Two people, Akshay and Bella, are tossing coins. Okay, and if you before the so you'll guess heads. Okay, then Bella will guess tails, and they'll just randomly think of something, and they'll just guess, right? They can't perfectly. They have no way of knowing what, because it's a fair coin. They have no way of knowing what is the outcome. So it's as random as it gets. The guess. So, but if you guess correctly, you will win the game. Okay. Now, Akshay, being a student of probability, notices that for 4 consecutive coin tosses, the coin is repeatedly showing tails.
But here, according to me, the deduction is not at all correct because getting a head or tail is always is a probability to be equal to 50%.
Okay, 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 great. Okay, yeah, we'll come back. Okay, and he calculates the probability of getting. He sees that okay, there are four consecutive tails, and he says that oh okay, so tails, 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 tails. I mean, tails have been coming so often. Okay, that it would be highly improbable if there's another tails. That's the probability of getting a fifth tail is very low. What is the probability of getting a fifth tail? Well, it is 1 by 2 power 5, right? There are 2 power 5. The sample space is 2 power 5. The size is 2 power 5. The sample space of tossing 5 coins. And then he plans on getting. So he says that this probability is so low that it needs to be that the next guy is heads, or at least like the probability of winning should be high for me if I guess another heads. So the question is his deduction correct? Like Tathagat said, it is incorrect, he's saying. And Ashutosh is saying student of probability needs to study about independent. Okay. Okay. So Ashutosh and Goyal is also saying all events are independent. Okay. And hence, so I think now that everyone is mentioning in the chat and as Tatagat explained, um, they are saying that it is independent. So all the events are independent. So I can't really tell whether the next one is ahead or not because they are purely independent. So your guess is as good as mine. But yeah, good. So I think all of us are convinced that his deduction is incorrect. But what is wrong in this point that it's highly improbable that I'll get another tail. That's what he's saying. No, it's 1 by 2 power 5. And this calculation is correct also. The probability of getting 5 tails is 1 by 2 power 5. So this is highly improbable event. So what did he go wrong with here? Tossing 5 coins, the size of the sample space is 2 power 5, right? Size of the sample space on tossing 5 coins is 2 power 5. And the probability that I'll get tails, 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 and then another tails is there's only one out of the 2 power 5 many cases. So it's 1 by 2 power 5. So what is wrong with his justification? If it is, if his deduction is incorrect, any idea?
No, I could not understand the question. So, are they flipping coins only 5 times or
See,
indefinitely forever?
so they flip coin 4 times, right? He flips a coin 4 times. They flip a coin 4 times, and they are getting tails, 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 tails. He notices that
Yes.
there are 4 tails, and if say there is a fifth tail, if there is a fifth tail, okay, what is the probability that I'll get 5 tails on 5 coin tosses? It'll be 1 by 2 power 5. And he says that this event is so improbable that I'll get another tails because the probability of getting 5 tails continuously is 1 by 2 power 5. That the the next coin, okay, cannot be a tails. It needs to be a heads, okay, or there is a very low probability that it's a tails. So what is wrong with this deduction? I agree with your the idea that you said about independent events, right?
That's true. That's true. But then 1 by 2 raised to the power 5 is the probability of observing continuous 5 tails,
Yes.
not the outcome of having fifth output as the tail.
Okay.
This is, yeah. So this is, I mean, this is something. So this probability is taking
Huh.
all the previous events into consideration and then So this is the probability of observing this entire stuff, and which has to be very very low.
Okay, okay, okay. Um, okay, Harsh is also saying Bernoulli's formula and so on. Yeah, so Argyle, what you are saying is it related to infinity space? Well, not really. Okay, I mean, yeah, there are some higher order mathematics you can talk about, like law of large numbers and all, which says that definitely you will need to say a head in finite number of tosses and so on. But um, here we are looking, the flaw in the logic is, okay, I think Goel, you mean the same thing, is that this is about getting tails, 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 tails. But what he says that the next guy should be a heads. But what is the probability that I'll get a heads on the? What is the probability that I'll get tails, 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 and a heads? The probability is still 1/2 power 5. So even if he's so it's not affecting. Betting on heads is not affecting at all, because it is equiprobable for you to get tails, 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 heads. What he's not understanding is that the probability mass is distributed across all the 2 power 5 events, and it's not unique for tails, 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 tails. Even getting heads, tails, heads, tails, heads is equiprobable. Even this is 1/2 power 5. And like Goel, you were saying, or Harsh, I think, was talking about Bernoulli trials, no? Yeah, is that he can
Yeah, Bernoulli's trials. Yeah,
yes, yes, yes.
मतलब कि success and failure का वो.
Yeah, yeah, yes, exactly. So you can ask, like, if I, what is the probability of getting fifth tails given that, previous four were tails? And now you can say that, okay, Bernoulli trials, uh, um, even here you are talking about independent events. Yeah, Harsh.
Could you please write down the formula? I'm actually forgetting that.
Oh,
Like,
okay. That formula I also don't remember.
okay.
Yeah, yeah. But yeah, it's not important for this case because it does not matter in this case. Okay, because it does not matter in this case also. Even if you take Bernoulli trials into account, these events are still independent.
Okay, thank you.
Okay. So because P is equal to 1 minus P. Basically, if you plug it into the formula, then you'll get that, okay, it does not matter. Okay. So yeah, this was the major flaw in the logic. And if you've seen this before, I mean, if you've seen, I mean, any version of this is what is called gambler's ruin or gambler's fallacy. Okay, why? Because it's similar to, gamblers in casinos and stuff, where they'll say that, okay, I've been losing so much, okay, then I must be able to win in the next time. Or they'll notice that, oh, okay, say they are playing something like roulette, and if they say that, okay, I've noticed that, okay, you know numbers 1 to 10 have not appeared for a long time, then I'll bet on one of those numbers. That is, but they don't take into account that the events are independent, and that's how, gamblers keep gambling and lose all the money. Okay.
Okay.
There's something called, is it inverse, or it's inverse gamblers ruin also, I think it's called inverse or reverse, I forgot. It's like, that is this fallacy. This is also a fallacy. This conclusion is not correct, that you walk into a room and you see that the person, okay, in the casino or arcade or whatever, they throw, let's say, 2 die and it lands on 6 6, and you assume that the person has been, it's just the opposite of this gambler's ruin process. Okay, you assume that the person has been throwing lots of die because the dice many times. Okay, he has been throwing the 2 dice many times, because the probability of getting 2 6s are so low that he has been he has been throwing the dice several times. But that too is, not true, because the outcomes are equally likely, whatever, whether it be 6 6 or 5 5 or whatever. Okay, great. Okay, now this is another nice one. Okay, what is the next question I have? Okay, these are two very nice questions. Okay, so the question is, 100 passengers board an airplane with okay 100 passengers board an airplane. Everyone has a ticket with an assigned seat number. However, the first passenger has lost their ticket, and they come in order. Okay, by the way, first passenger, second passenger, they all come in order. Okay, and the first passenger has lost the ticket and takes a random seat. Okay, that seat could be the one he is assigned to, or it could be any other seat. Okay, now every subsequent passenger attempts to choose their own seat, but if they see that their seat is already taken, then they'll take a random seat. Suppose you are the very last passengers to board the plane. What is the probability that you will get your assigned seat? I'll explain again. Suppose there are passengers P1, P2, P3, and so on till P100, and you are the 100th passenger. And P1 is assigned seat S1, P2 is assigned seat S2, and P3 is assigned seat S3, and so on till S100. Okay, equally likely event. Okay, these are the passengers, and these are the seats. Okay, now P1 is assigned seat 1. Okay, so is this a kind of derangements? Okay. Okay, good question, but I've not mentioned derangement yet. So this is seat 1, seat 2, and so on.
Now, sir, basically,
Yeah, just hold
according
on.
to
So Tathagat,
ac-
have you seen this question before?
no, not yet,
Oh,
but
not yet. Okay.
problems like that I have solved before.
Okay. 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 Okay.
So from that kind of concept, I can say you that uh, if the first passenger seat is chosen, the other passengers will be unable to find their assigned seats.
If the first passenger choose a random seat, no, that's what you mean.
Yeah,
Okay. Yeah.
yeah. And if last
No, but
passenger seat is
yeah. Yeah.
chosen,
Huh.
then the last passenger will be unable to get his or her assigned seat.
Yes.
So, if we consider the events to be equally likely, then according to me, the probability should be 50%, like that.
So what you mean is, um,
Like this process continues for until the first passenger seat or the last passenger occupies his or her seat.
hmm, hmm, hmm. Yeah. Yeah. That is going in the correct lines. Okay. 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 Good. Yeah. So, but I was explaining the problem. Okay. So you have seat. Okay. So the first passenger is assigned seat 1, but he lost his ticket. He does not know where to sit. So he everything is equally likely for him. So with 1/100 probability, right, he will sit in one of the seats. Now he could have gotten his own seat. If he had gotten on his own seat, everyone else has their everyone. Okay, Harsh is saying correct answer is 1%. Okay, good. So let's see. So the first passenger, the second passenger knows his seat, right? So he sees that okay, S2 is unoccupied, I'll sit on S2, and third passenger also knows that he needs to sit on the third seat, S3. So he'll say this is unoccupied and I'll sit, and everyone sits on their own seat, and finally you will also sit on your own seat. The problem arises if the first passenger, since he has lost his ticket, he sat on a random seat. Let's say he sat on seat number 21. First passenger sat. Now there is chaos. Okay, because now the 21st, okay, this P1, P2 will sit on their assigned seats. P2, P3 will sit on their assigned seats. As soon as the 21st person comes in, he looks at seat 21 and he sees that it's occupied. Now he's panicking. He needs to sit in one of the other seats randomly, and he sits on a random seat. And now you risk the chance of losing your seat, right? What is the probability that you'll sit on your current seat? That's the question. Okay, and Harsh is saying 1%. Okay, and Tathagat is saying 50%. Harsh is saying 1%. So any other guesses? Just close the door. Yeah. Okay. The question is clear, no? Hello, I'm audible, no? Okay. So the question is clear, I hope. Okay. Yes, the question is clear. Okay, yes. So I mean, you can guess. Okay, first maybe you can guess whether it is less than 50% or more than 50%, less than 1%. Any idea? Any guess? Less than 50, Ashutosh. Okay, okay. Okay. And rest, Goel, what do you think?
Yeah, I also think this is less than 50%. Certainly, it won't be 1%. 1% would mean that only one person is selecting this thing. I mean, this seat which is reserved for the 100th passenger. But then, so actually, this problem is very interesting. To what extent the error is going to be propagated?
Yes. So to what extent
I
is the
think,
error getting
yeah,
propagated? Right.
yeah, I think it would be less than 50%.
You think it's less than 50%? Okay. Okay, let me first clear one side of the doubt that Aru Pratap Singh is also saying 50%. Okay, I'll at least tell you that it is at least 50%. Okay, first. Why? Because the first person, S1, um, is going to. It also depends on number of seats, people boarding. Okay, that's a good point, Angita. So you are saying 50%, but there are 100 seats. No, what if? So then is 100 magical that you are getting 50%? Okay, okay. So let's just okay. I'll should I? Okay, I'll tell you the answer also, but let's just exhaustively. Let's say there are only two seats. So there are only two passengers, P1, P2. So P1, okay, has S1 assigned and P2 has S2 assigned. Now P1 loses their seat, ticket, right? So P1 can, so this is S1, this is S2. So first option is P1 chooses the first seat, okay, since his outcomes are equally likely. P1 chooses the first seat, and you need to sit on your own seat, which is a good thing. Now P1 chooses your seat and then you are sunk. So this is the bad case. So what is the probability with which you are getting assigned your own seat? In your case, the answer is in this two wala case, it's half. What if there are 3 seats? Seat 1, seat 2, seat 3. Now let's look at the possibilities. The he sits on his own seat. Okay, person sits on his own seat, and person 2, okay, person 2 comes and sees that, oh, his seat is still unoccupied, and he sits on his own seat, and then person 3 also sits on his own seat. Okay, and otherwise what happens? Otherwise person 1 sits on this seat. Okay, person 1 sits on the middle seat, and then person 2 sees that it's unoccupied. So there are 2 cases possible. He sits on your seat, and person 1 is already sitting here. Okay, and then you are forced to choose non-seat. So this is a bad case, and this is a good case, right? And here what is the outcome? That he chooses the last person 1. Oh sorry, person 1 is already choosing this. Person 2 chooses the first seat, and you are finally left with your own seat, and then you are good. And finally, the third outcome is when person 1 chooses your seat. Okay, person 1 chooses your seat, and then again there are 2 possibilities, but 2 possibilities are equally bad. So you have person 1 sitting here, person 2, person 3, or person 1 sitting to your seat, and then you have person 2 sitting here, person 3 sitting here, and these are both bad. Bad, good, bad, good, and there should be one case that we are not investigating. One case we are leaving out. Or is it in relation to even, odd? There's no randomness here. There is a randomness component here. There's a randomness component here. Huh. So you have 3 bad and 2 good outcomes. Can't we solve this with normal calculation? You can solve it with normal. Oh, no, Harsh, this problem, I'm just showing you an example. Okay, I'm showing you the exhaustively. You can actually solve it in one shot. Okay, you can solve it in one shot with a quick analysis. Okay, but somehow I'm leaving one case out here. I'm thinking maybe it will split in 2 here, or is it the fact that I'm taking it as odd, the number of people as odd? Is this happening? I think if I take it as 4 people, then it will work out. But okay, I'll tell you this much. Okay, because we don't have much time. I'll tell you this much, that the answer is 50%. It does not matter how many people you take. The answer is definitely 50%. I will give you a hint. Okay, we'll discuss it next time maybe. Okay, you can think about it offline. I'll give you a hint. Think of these things, that every person is assigned a seat. Definitely. So if you let 98 people enter, then 98 seats occupied. Okay, 98 people entered, 98 seats occupied. So what does that mean? 2 seats left. and these two seats may have your seat or may not have your seat, and may have the 99th person seat or may not have the 99th. Analyze these cases. There will be two seats left, right? It could be like the S42 and S100, say, or it could be some other configurations, but focus on the fact that there are only two seats left and analyze this case. And finally, it boils down to only whether you get your seat or not. So it does not matter that there are 100 people. Like I think Tathagat said, no, the burden of this probability randomness will actually propagate forwards, and it will become a smaller instance. Okay, for example, if the first person, okay, if the first person P1 sits on P21's seat, okay, S21 sits on S21, seat number S21, then it means that P2 sits on S2, P3 sits on S3, and so on till P20 sits on S20, and then when 21 comes in, that is where, so now you can treat this as a smaller problem. No, this becomes this becomes a smaller instance of the same problem. So P1 sat on 21, all these seats are gone, all these seats are gone. Now it is identical to the previous problem, that these, the persons labeled P22 till P100 enter the aeroplane. What is the probability that P100 gets his own seat? It is the same problem but lesser number of people. And then 22 may choose to sit on his own seat or choose a randomly seat. And then when he chooses that random seat, the problem becomes smaller. Now again, the question is, whether you get your own seat or not. Okay. So it is ultimately me exchanging a seat with a guy or not. Exactly. It is whether you exchange a seat with your guy or not. So think about this. Try it. Try your hand at it. Okay. And yeah, Harsh.
Show the question.
Oh yeah, sure. You will take a screenshot.
Thanks. Yeah.
Okay. I'll remove the markings. Okay, done. Okay, now okay, so this is another interesting question. Okay, it's already 8. Okay, we'll discuss it first thing next week. Okay, but I'll give you the question. Okay, I'll explain the question. Ramu, the local drunkard, is standing one step away from the edge of the cliff. Suppose at any point of time, the probability of stepping away from the cliff is P and towards the cliff is 1 minus P. Okay, what is the probability that he falls off the cliff when P is half? Okay, so what I mean, what is meant by the problem is here. Okay, so think of this one-dimensional line. Okay, and these are the steps that Ramu can take. And Ramu is standing here, one step away from the cliff. And at any point of time, okay, he can move left and right. At any point of time, not just here, but at any point of time, he has the probability P of stepping away from the cliff and 1 minus P probability of stepping towards the cliff. Okay, at any point of time. Question is, what is the probability that he falls off the cliff whenever P is 1 by 2, when P is 1 by 2. Okay, so forget about 1 by 2 for now. With P probability he moves away from the cliff. 1 minus P probability he moves towards the cliff. What is the probability that he'll land up here and then fall? Landing up here means he'll fall, by the way. Okay, landing up here means he'll fall. So of course it's not half, by the way, because you might say that he has one half way of stepping here, so he'll fall by a probability half. But he could also have moved like this and arbitrary ways to the right, and then come here and fall. Okay, Tathagat is saying this one is interesting, tough one to crack. Okay, yeah, this is a very interesting problem. Yeah. Okay, so he of course he has half probability of moving here, but he also has more probability of moving falling, because he could like move in arbitrary ways and then fall here, or maybe like he keeps going to the right and left and right and left, and he keeps going on and he never falls. That sounds like a very probable event, no, that he will never fall. So again, I want you guys to guess first. What do you think is the probability that he'll fall? So let me call this 1, 2, 3, 4, 5, 6, and so on. Okay. Now what I'm going to ask you is, what do you guess is the probability that Ramu falls? When P is half, meaning with equal probability he is moving away from the cliff, equal probability is moving towards the cliff. Okay, starting at let me call this x, this x. Okay, x is the distance from the cliff, starting at x equals 1. Okay, any guesses?
What is the limit, like, go to the right side?
It's very large. It's very large, so you can think of it as infinity. So for this problem, if you take the limit to be very large, okay, it will not matter. So infinitely stretching towards the right. So which makes it even more probable that he will never fall, right?
Yeah.
Right? Yeah. So yes. So what is the guesses? Okay, Ashutosh Jha will say will fall, but what probability? With what probability? So Ashutosh, I just want to clarify, with what probability will he fall? I mean, like, even if you have a guess, that's okay. You don't need to justify it yet. Okay, 50% probability. So, but yeah, this, okay. So 50% probability he'll definitely fall, because 1 minus p. But he could also, so is there no chance of him moving like this, and then falling? That'll add to the 50%, no? So maybe the right answer is something like 60, or maybe 50.1 or 55 or something like that, because some additional probability will be here that he moves like this and then falls, right?
So what is the sum of the GP, like 1/2 plus 1/2 square plus 1/2 cube kind of the thing
What
density?
kind of GP? Where is GP here?
So GP here in the sense that he makes a move to the, say, goes till 3.
Huh?
So probability of going till 3 is 1/2 square,
Huh?
and then returning back here. So again will make 1/2 square, 1/2 so 1/2 raised to the power 4,
Okay.
and then
Oh, okay,
takes a move.
okay. I see what you mean.
So I mean, if we consider all possible cases, that probably that would be the sum of the GP, like
Yes, but
half plus.
the GP will go infinitely. It will be an infinite sum, no?
So even for the infinite sum, the probability came out to be 1. I mean, this sum came out to be, what's the sum of, if the first term of the GP is half, And then if we go still infinite, so half and then 1 minus half, the value came out to be 1. So it's pretty sure that he's going to fall with the, definitely going to fall with the 12.
Okay, okay, nice. Okay, okay. So I'll reveal to you the solution at least. I mean solution as in like the final answer. Maybe the calculation we can do next week because we are getting late. Probability that he falls is 100%. It's very shocking. It's very shocking. And very surprising that, yeah. So, and sad for Ram. Yeah. Okay. So, this answer is 100%. And Tathagata das answer. So, yeah, and so there's a neat. You can try to do. Yeah, Harsh.
I have a question. At any given point on the Cartesian
Okay.
that you have done, 1, 2, 3,
What it?
4,
Yeah.
at any point,
So what it means is
falling off the cliff is 1 by 2, right?
no. Not at any point. For example, if he like moves like this, okay, and like this, he's here. Now to move back, he has half probability of going here, and to move back, he's half. If p is half, okay, that's what.
Okay.
So the probability that he'll fall off the cliff would be like half times half or something like that. No, so you'll expect this probability to be small. Firstly, when he was here, I agree he has half probability of falling. So it'll be half plus something, and this something you'll expect it to be small, right? But
Come again?
so what I mean is, he is starting from this position 1 with half probability. He has a probability of moving left. With half probability he's moving right, but if he moves left he'll fall. So probability that Ramu falls starting at x equals 1 is the sum of probability that Ramu moves left, in case he'll definitely fall, plus the probability that Ramu um, plus probability that Ramu falls on moving right. Right? And this Ramu moves left is definitely half, which is half plus this probability. You get it? So half plus this probability. Okay. But I also said probability 1. Yeah. Goel, that logic is also correct. That logic is also correct. You okay? I did not try it using GP. I thought using GP would be um, you'll deal with infinite sums and then it will be a problem. But there is an alternate way to do alternate calculation way to do it, which is very neat.
Okay. Yeah,
Okay.
fine.
I'll show it to you guys on the next session. So you'll deal with using some kind of recurrence, but it's still simple and very elegant. Okay, the way to actually calculate it. So yeah, so Harsh, I was just saying that okay, so the probability that Ramu falls on moving right is half plus a dash, and this dash you'll expect it to be small, but surprisingly the total probability is 100%. It's not 51, 52.
Oh, so it's basically that GP sum.
It is, yeah, but that's what I'm saying. If you can do it the GP way, or you can do it some other way. Okay, I'll tell you the other way in the next class. Okay.
Okay.
Okay. Yeah. So yeah, I'll discuss it in the next class. This is also an interesting problem, but you may have seen it before. It's about derangements. So if you've already seen derangements, it's not surprising. So any other thing is there? Oh, by the way, this is called the one-dimensional drunkard's walk. Okay. Comes up in randomized. Can you show question number 1? Joined a bit late. Sure. Okay, Renuka. Yeah. And yeah, for the others, we've come to the end of the session. Okay. So the next session will be happening on um, Tuesday, 6 p.m. again. Okay, as always. Yeah, okay, good. Yeah, and see you then. If you have any more questions, just let me know. Oh, yeah, Tathagata. Thank you for attending. Yeah, yeah, and I'm glad that you liked the session. Yeah, thank you, Asutosh. Oh, thank you, Varsh. Thank you, thank you. Okay, thank you, Renuka. Okay, good night. Yeah, thank you, Ankita. Okay, thank you, Enes. Thank you, Ankita. Yeah, I think I've kept you guys for quite some time. So you guys must be quite hungry. Okay. Yeah, I'm glad it was worth it, Ashutosh. And yeah, I'm very sorry for the technical error also. I forgot to tell. But yeah, thanks for being so patient. Okay, if okay, great. Thank you, Ankita. Thank you, Ashutosh. Yeah, thanks. Okay, uh, I will be ending the session now. Okay.